So there was a question on how one would go about defining the invariants of a vector. It's relevant, and it's particularly relevant because as we go deeper into the subject, we're going to talk in terms of invariants of tensors. The notion of invariance of a vector is not often used, but there is something that is invariant about a vector. In particular, the magnitude of a vector is invariant with respect to basis. Okay, so let me put that down. The magnitude of a vector is invariant with respect to basis. Okay? What this means is that we all know what we mean by the magnitude of a vector, right? So if we write that as magnitude of u, right? We all know, of course, that this can be written as the square root of u I ui. Okay? This is indeed an invariant. And to see how this happens, what one has to see is that this, of course, is also equal to u dot u. Okay? Right? What this implies now is that if we write u as ui ei, really it implies that for u written as ui ei, okay, we know then that u, the magnitude of u, which is then the square root of u dot u, which can be written again as the square root of ui ei dotted with uj ej, right? So we can write this then as ui uj delta ij, which is square root of ui ui. Okay? Right? Now, another way of writing this, of course, is also to write it as u equals u bar I e bar I. Right? Go through the same steps as above, and what one will see is that this implies that the magnitude of u will also turn out to be written as u bar I u bar I. Okay? So the magnitude is, it has the same formula independent of the basis of representation. Okay? And this is what we would consider to be an invariant of a vector. Okay? Other properties that are invariants are not really the vectors themselves, but there are operations whose results are invariant, right? So the result of the dot product is invariant with respect to basis. Likewise, the result of the cross product is invariant with respect to basis. Okay? So we saw that the magnitude of a vector is an invariant of the vector. There also is another property of a vector that's invariant, okay? And that is its direction. And here's how that works. So we have our vector u, okay? And let's suppose we are going to expand it in terms of a basis, right? Let's suppose that u is ui ei. Let's suppose that in addition to u, we also have another vector n, okay, n also belongs to R3, right? It's also a vector in 3 dimensions. And we know that we can then write n as ni ei. Okay? And n is a unit vector, so magnitude of n is 1. Now, once we have this, we know that we can write, let's suppose we say that cosine of theta is u dot n. Okay? Divided by the magnitude of u. Okay? Now, this particular quantity, the cosine of theta defined as this, is also invariant. Okay? This is also invariant with respect to basis. Okay? What this means is that if we write u by expanding it in terms of a different basis, u bar I, e bar I, and likewise we do the same for n, right? We also expanded it as n bar I, e bar I. Okay? What this implies is that cosine theta is also equal to, which we know is u dot n divided by the magnitude of u, can now be written in terms of two different bases, right? We can write this dot product either as ui ni, and then we can write this magnitude as, we can write it as the square root of ui ui, where the sum on I is implied. Okay, so this is all in terms of the basis ei. If we write this in terms of the basis e bar I, we have u bar I n bar I divided by square root of u bar I u bar I. On the previous slide, we saw that these magnitudes are the same. Okay? It turns out that because of this invariance property of the dot product, the numerators are also the same. Consequently, this direction of u relative to our unit vector n is also invariant. If we write u, if we draw u as that, and we say that this is n, where we recall that n is of unit magnitude, right? That is the angle between them, theta. And the whole point is that this angle, right, which is essentially a direction, is invariant with respect to bases. It does not matter whether this is the basis we are looking at, right, E1, E2, E3, or that is the basis that we are interested in. Okay, so what we see that the magnitude and direction of a vector are invariant with respect to bases. Right? But then that should make you think a little more. The magnitude and direction of a vector are invariant with respect to bases. But what does a vector have in addition to its magnitude and direction? There is nothing else, right? So if those two properties which completely define a vector are invariant with bases, the vector itself is invariant with respect to bases, right? So this implies that the vector is invariant with respect to bases or bases. And this is what we mean by the invariance of a vector. Okay, this is the property of invariance that a vector has. It doesn't matter how we look at this vector. If we look at it with respect to this basis or a different basis, the vector is the same because, as you can see, the magnitude of the vector and the direction in which it is pointing remain the same regardless of what basis we want to express its components in. Okay? And this is essentially this property of vector invariance.